No, there's something wrong with your mic.
Can you hear me now? I have a problem, yes, with my mic. That's why I open my phone for like 5 minutes. Then I will open back the mic. Can you hear me now, guys?
Yeah.
So last time we finished auto cycle, which is we said all of them. We have compression. All of them. We have heat addition. We have expansion. We have rejection, exhaust. All of them. We have 4 processes. Always, all of them. Auto, diesel. They will, of course.
Professor, there's a loud buzzing noise coming from you.
I don't know. How about now?
Still the same.
I will try to be away from the computer. So compression and expansion always isentropic for all the cycle. So delta S equal to 0. So 2 cases. If it's ideal gas, which was all the cases, ideal gas, we just have P proportional to V to the K. If it's steam table, we're gonna have delta S equal to 0. Just 5 minutes, I will open my mic. Just 5 minutes to charge a little bit. So here we have all the cases was ideal gas. So compression and expansion always isentropic. Otto, diesel, they will even in Carnot cycle and some of the special cycles. The change was in heat addition and heat rejection. For Otto, constant volume, both of them. Heat addition, that's why we said CV delta T, CV delta T. So 1 to 2, 2 to 3, 3 to 4, 4 to 1, and go back. It's a cycle. The first process and the third process always isentropic. Is that clear, guys? Always isentropic. Why the heat addition and heat rejection was constant volume or pressure or temperature. Temperature was Carnot cycle. Volume Otto cycle. Constant pressure and constant volume diesel cycle. Some part constant volume, some part constant pressure, they will cycle. Now, if we have both at constant pressure, we call it Brayton cycle. So Brayton cycle is different than other cycle. It's like jet engine. Jet engine, it's exactly Brayton cycle. This is constant pressure, heat addition, and heat rejection. Sorry guys, I'm gonna open it in a few minutes. I know I hear the noise I missed now. Okay guys, sorry for that. So jet engine look like this. We have compressor, combustion chamber, turbine, we have drum it in the air. And go back, compressor. For example, Rankine cycle, we will have pump, boiler, turbine, condenser, and go back, and so on. So let's go now, Brayton cycle, section 9.8, the last section in chapter 9. Then we go ahead and chapter 10, and that's it. It's still gas. It's still gas. Ideal gas, maybe air, maybe something else. Ideal, like carbon dioxide, usually air, but sometimes not air. So Brayton cycle, chapter 9, one of the cycles after Otto, diesel, Ericsson. We have a lot of cycles. So this is one of them. We focus on only 5 special cycles, and this is the 51 or fourth one in chapter 9. So Brayton cycle like this. A jet engine. What happened in the engine? It's a compressor. So we have here 1, 2, 3, 4, and go back to 1. So here 1, compressor. We have combustion chamber, CC, combustion chamber, turbine. Okay, guys, can you hear me now? Go. No problem now. I think no noise.
Yeah,
So,
that's so much better.
Compressor, combustion chamber, turbine. So isentropic, constant pressure, heat addition, expansion in turbine, then heat rejection at constant pressure. So now in Brayton, even like B, constant pressure, O2 and diesel, O2 was constant volume both, diesel one part is constant pressure, another part at constant volume, but Brayton is constant pressure, which like this engine. So the other cycle was piston cylinder. The other cycle, like the car, the piston cylinder. Compression, expansion, heat addition, and so on. But now it's like this. Air comes, some fluid come, compress, burn, expand, get jet. Drive your airplane, push your airplane, and you get thrust. The force needed to overcome the drag, the aerodynamics drag on the airplane. So this air comes with high specific volume, or actually more expanded. Then it compress, burn, expand, get work, get power, then reject. If you plot it in the, let's start with TS diagram. I like the TS diagram more than BV. TS diagram, any one of them. So guys, where do you think we started here, and where do you think we started here? Here, guys, where? Bottom left or right?
Bottom right.
Bottom right, here. Let's say this is one. How about here?
Bottom left.
Exactly. We have low temperature, low energy, low entropy, and we're gonna burn. We're gonna increase. That's why we go to the left. Here, we're gonna compress. The pressure will increase. That's why we are down. The volume will decrease. That's why we are right. So we're gonna compress. Isentropic, constant entropy. Here is so clear, vertically. All of the cases, 1 to 2 is vertical. All the cases. Heat addition, constant pressure. So we're gonna have something like this. Like exactly, like what, guys? Like who? Diesel. Diesel was constant pressure, heat addition. Then we're gonna have turbine, which is here, isentropic, vertically. Something like this. Today, I'm gonna discuss the most important physics in this problem. Why you are getting work. I'll give you why, guys. If you plot the PV diagram now, PV diagram, this is isentropic. I'm compressing, so the pressure build up, the volume decreasing, of course, like this. This is 2. Then I'm getting at constant pressure. How it look like, guys? Is it vertical or horizontal? Vertical, horizontal in the PV diagram. Constant pressure.
It's horizontal.
Exactly. So from now on, you can expect what is going on. Ah, that's horizontal, of course. Heat addition. Then expansion isentropically. This is isentropic. This is pressure constant. Usually, if something is not straight, like vertical horizontal, we write is not straight or vertical horizontal, we write the B constant. So we have here isentropic expansion from 4. Where is 4, guys? This is constant pressure. So it's horizontal or vertical? Constant pressure.
Horizontal.
Exactly. So it's supposed to be along this line. So it's here, of course. So 4 to 1. So 1 to 2, 2 to 3, 3 to 4, 4 to 1. This is, I don't need to write constant pressure here, but I need to write it here. This is, of course, isentropic. delta S is 0. Or 1 and 2 isentropic. Like for example, B2 over P1 equal T2 over T1 to the power K over K minus 1, which is 3.5, for example, for air. The same 3 and 4. B4 over T4 equal P4 over. So you can cite here, this is isentropic. Isentropic means P4 over P3 equal T4 over T3 to the K over K minus 1. That's always if it's isentropic. Ideal gas at every state PV equal RT. At ideal gas low, PV equal RT. That's always correct. That's always correct. So the difference here, guys, this is constant pressure. This is the whole idea of all these cycles, guys. Look at this. We pay compression. We pay this distance. And we burn fuel. Then this is W compressor, for example. W compressor, very obvious. Can be rate, can be not rate. The heat addition. Then we get W turbine. Then we have Q low or heat rejection. As you can see, guys, here, the pressure lines in the TS diagram are diverging. The pressure lines are diverging. This spacing increases with like temperature or bigger entropy, for example. So this spacing, guys, increases. Pressure lines are diverging. This is the most important keyword you're gonna hear here in this course. The pressure lines are diverging. It means if you compress here, you're gonna pay less. We wish to go vertically, yes. If you expand here, you get more. So what will happen? I will take part of this length, exactly this length. So what is this, guys? From here to here, this is to pay the compressor. The remainder is W dot net. For example, in jet engine, it's a thrust. The pressure line diverging. I pay here less, I get more. This is like Rankine cycle later. So the pressure lines are diverging. So why I go from here to here? Why I add fuel? To go to bigger spacing between the lines. I wish to go smaller. Back. So I pay less. Then I burn, I get more. Some of this work to drive the compressor, usually the compressor is connected to the same shaft of the turbine. So some work of the turbine to drive the compressor, and the rest is called W net. So W net, it's either Q high minus Q low or W turbine minus W compressor. So it's either Q high minus Q low or W turbine minus W compressor. This is the net out work. If it's dot. Per unit mass. The small. Okay, guys? Does it make sense? The pressure lines are diverging. Okay, guys? Is it clear now? Can you hear me, guys?
Yeah, we can hear you.
So this is the whole idea. The pressure lines are diverging. This is the key word for all the engines. The lines are going away. That's why compress isentropically, burn, expand, compress, burn, expand. Okay? So This is, let's analyze this engine as the same way as we did in Otto and diesel engines. Me?
You're echoing.
Yeah. No, there is no more echo. Don't worry. I close the other one. So here, the idea is we have the pressure line are diverging, getting away from each other. That's why we pay less here and get more here by burning this. So guys, I compress here, let's say 100 watt. Then I burn. Then I get here, let's say 150 or 200. So I get 100 to run this, and the rest, let's say 80 as an output. So what I paid, guys, to get this, what I paid to get this 80 watt, this part, this distance is the same as this distance. So the rest is our output. So what I paid to get this, guys, what did I pay? Someone tell me, what did I pay to get this 80 watt? What did I pay? Of course, I paid something. I need to put some money somewhere to get this. So the compressor driven by the turbine, and the remainder of the turbine is an output. So what did I pay to get this, guys? What the money? Where is the money is? What did I pay? Energy can be neither created nor destroyed. Can you hear me, guys? So there is some energy I paid. Where?
Is it an input of 80?
What?
80?
Yes. Yeah, what did I pay? This is an output. What did I pay to get this 80?
Just the work of the compressor?
No, this is already driven by this. So this part, this, like, if we have conversion turbine, always the turbine. Part of the energy to drive the compressor, the rest is output. So from where I get this output, the remainder? From where? What did I pay, guys?
80 plus work compressor?
What did I pay, guys?
Is it 80 plus the work compress?
What did I pay? Pay, it means this. This is what I pay. I pay fuel. I burn fuel. I get this and this. This drive this. This is mine. So this one came from. If you do not burn, you're not gonna get some. If you imagine you compress and expand, nothing. Okay. So this is what happened in ideal case. In reality, no, that's not correct. In reality, this we have losses. You remember when we talk about this? And we have losses. You talk about this. So this guy, in reality, go a little bit like this. This guy, in reality, go do it a little bit like this. It means I get less in the turbine. I pay more in compressor. Does this happen in reality? I pay more in compressor. I get less in turbine. But for now, we're gonna assume it's ideal. So isentropic. Unless I have problem with compressor or turbine. So make it easy for you. So in reality, in ideality, we're gonna assume ideally this is vertical, this is vertical. This distance, exactly T3 minus T4, is the work. Like the work turbine is CP T3 minus T4. And here work compressor is CP T2 minus T1. So this distance, assuming CP is constant, this distance exactly like work, and this distance exactly like work. Part of this work to drive the compressor, and the remainder is my net out force, which is due to this payment. I paid that. The engine, we pay fuel by tons, 50 tons for the airplane to drive from one city to another city. 100 ton. Like this is a big number, a lot of money, almost, I don't know, 1/3 of the cost of the travel just due to this, the payment of the fuel. Do you know what the fuel we use in the airplane, guys? What type of fuel? Does anyone know what the type of fuel we use in airplanes in the combustion chamber?
The jet fuel.
We use kerosene. You know kerosene?
Yep.
It has some advantage because it's less volatile. It's not that much efficient, but it's less volatile. So in terms of commercial cost, it's much better than others. Other fuels are highly volatile. That's why we prefer in the jet engine, in airplanes, or even turbofan, turboprop engines, we use kerosene because of its less volatility compared to the other fuels. Anyway, so Brayton cycle, it's an open cycle. Unlike others, closed cycle. Closed cycle is Q minus W equals delta U. Do you remember this, guys? And if it is constant pressure, we can say if it's constant pressure, Q equals delta H. If it's only constant pressure, like the heat addition in diesel engine or the last part of the engine. Here, everything is open. Forget about this law. Q minus W equals delta H. This is already the equation. Q minus W equals delta H. Here, there is no heat, but we have work. So the work, delta H. Here, we don't have work, but we have Q. Q is delta H. Here, we don't have heat. We have work equals delta H. Here, we don't have work. So the Q equals delta H.
Professor,
Yes.
could you write the that in a different color?
Yes,
I can't see it. Sorry.
Yeah, that's secret. So this is W, Q minus W equals delta H. Is it clear now?
Yeah.
So this is the first law of thermodynamics for open system, assuming, neglecting a steady state, of course, and we have neglect all the kinetic energy and potential energies, and it's steady. So this is input and output. H1 minus H2, H3 minus H1, and so on. This is input minus output. Because it's open system, open cycle, open system. Unlike closed system in Otto, diesel, dual, Carnot. So here W, so this equation applied here, 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 here. Here, no heat, we have work, W compressor. Here, we have heat, but no work. We have work, no heat, W turbine. Here, we have heat, no work. So WQ, WQ, W compressor, W combustion chamber or high, so Q, W turbine, Q low. So W compressor here delta H. W combustion chamber is delta H. W turbine is delta H. W Q low is delta H. For all of them delta H. 1 to 2, 2 to 3, 3 to 4, 4 to 1. All of them delta H. WQ, WQ. If we assume CP is constant, CP constant, so delta H just CP delta T. Delta U, if you want it, CP delta T. We don't want it here. We don't want this here, but we want delta H. So here, just CP delta T. CP delta T, CP delta T, CP delta T. So the whole idea here, guys, to be able to get all the temperatures at every point. Again, because this is 4 processes, we need 4 inputs, just 4. We need 4 inputs. For example, I give you P1, T1. The compression ratio, which is here pressure ratio, P2 over P1, which is RP. P2 over P1. This is P2 over P1. We'll discuss this later. For example, T3. If you have these 4 inputs, you can get everything here. Just 4 independent variables. You can get everything in this cycle. You can get the work, you get efficiency. Let's do it. So you got, guys, the compression 1 to 2, what's going on? 2 to 3, 3 to 4, 4 to 1. You know what's going on here, correct? Okay, guys? Before we solve, we can derive the thermal efficiency in the same fashion we did for Otto and diesel. So eta thermal is equal to, let me open the lecture notes to follow the same lecture note. Brayton cycle. Yeah, we have Q in, Q out. The cycle, heat addition. Okay. So we have eta thermal is 1 minus Q low over Q high, which is equal to. Guys, here, what is Q low, guys? Somebody tell me what's Q low? Between 4 and 1. All of them delta H. Q or W is delta H. So what is Q low?
CP delta T.
Exactly. Perfect. You are great. CP delta T. What's T minus what? Always bigger minus smaller. Always. Without thinking. So which one minus which one?
3 minus 2.
Nope. The rejection. So 1, 2, compress. 2, 3, heat addition. 3, 2, 3, 4, turbine. 4, 1, rejection. So what's minus what's Q low? It's rejection. The last stage. You have 1, 2, 2, 3, 3, 4, 4, 1. Compressor, combustion chamber or boiler. We have here turbine. We have 4 to 1 rejection or heat condenser, for example, rejection. So which one Q low? This is compressor. Q high, W turbine. So which one minus which one?
T4 minus T1.
Perfect. Bigger minus smaller, always. Look at the chart. This is temperature bigger than this. This bigger than that. This bigger than that. This bigger than this, because the curve has slope. So of course T4 bigger than T1, of course. So T4 minus T1. Here T high. Somebody tell me what is Q high? Heat addition at the compressor. Is it CP or CV?
The 3 and 2.
Yes, but CB or CV?
Should be CP, right?
Exactly. Everything is delta H. CP. Be confident. This is CP, doctor. This is delta H. Everything is open. Q minus W equals delta H. Okay?
So does that mean both values are CP?
Of course. That's constant pressure heat addition. Constant pressure heat addition. Constant pressure heat addition. Even if this is like this, it's CP delta T gives you how much heat you paid. You have energy of a state, became another state. Because you add heat at constant pressure, that's why we call this. Okay? This is definition of CP. It's heat added to the system at constant pressure. So of course, CP delta T. Correct? And even if you have mass flow rate, you will cancel. So this will cancel, this will cancel. Now, you can take T1 and T2 common factor. So it's 1 minus T1 times T4 minus over T1 minus 1 over T2 over T3 over T2 minus 1. You will find this equal to this from isentropic relations and pressure equals. And this guy is T2 over T1 is P2 over P1. This is to the power K minus 1 over K, which is RP. So it's 1 over RP to the K minus 1 over K. Exactly same as the Otto cycle. But Otto cycle was volume ratio, was R to the K minus 1. Here is RP to the K minus 1 over K. So R was volume ratio, R was V2, or actually V1 over V2. Here R is P2 over P1, which is RP. This is called compression ratio, compression ratio. This is pressure ratio, this is compression ratio. Pressure 2 over pressure 2 is higher. Here pressure 2 is low, volume 2 is lower. When you compress, pressure increases, volume decreases. This is RP, this is R. Okay, guys? Make sense? If you don't understand, let me know, guys. I can explain it again.
Can you go over it again, please?
Sure. You know 1 minus T4 minus T1 over T3 minus T2. We take T1 common factor, T2 common factor. Between 1 and 2, we have isentropic. Isentropic means T2 over T1 equal P2 over P1. This is the K over K minus 1. And this pressure ratio is exactly the same as P3 over P4 because P2 equal P3, P1 equal P4. So this pressure ratio is the same, which is equal T3 over T4 to the power K over K minus 1. If you equate this with this, you will see this guy cancel this guy. T4 over T1 equal T3 over T2. So this guy equal to this guy. It's a ratio. If you remove these powers and replace T3 down, T1 up, you will see this ratio minus 1 equals this ratio minus 1. So the remainder is T1 over T2. T1 over T2 is P1 over P2 to the power K minus 1 over K, which is 1 over RP. K minus 1 over K. 1 over RP because T1 over T2. You need P1 over P2. Okay? So idea here is so simple. Let's solve a problem. Before we go ahead, let's solve a problem. The problem 99. Please read problem 99. Read problem 99 in the textbook. Let's solve a problem. Usually, we are engineers. We understand more when we solve. So sometimes, if you have confusion, if you have solve it, you will understand. If you, for example, you cannot understand, I don't know, control system. If you talk about, like, I don't know, do you have control class or not yet, guys? Do you have control class? Like control system, dynamics?
No.
Okay. You have fluid mechanics?
Yeah, it's upcoming.
Okay, upcoming, not yet. So if you know, for example, fluid mechanics, sometimes when we solve a problem, we understand more by solving, by applying, by exercising. So when we solve this problem, we'll see a lot of things we have mentioned implicitly in the link or even explicitly, but was not clear. It will be more clear. So what happened, guys? We have problem 99 in the textbook. In the end of chapter 9, we have an AC engine, aircraft engine, not AC like air condition. It's a Brayton cycle. It will be mentioned explicitly Brayton or Otto or diesel. So focus on the equations given for this cycle. It was, I think, was air. Yes, was air. So it's compressor, combustion chamber, turbine. He said, I give you mass flow rate 1 kilogram per second. Okay. RP, pressure ratio 10, which is P2 over P1. You have P1 and 70 kilopascal, and you have T1, which is 0 Celsius. It's altitude, let's say altitude of, I don't know, like 30,000 feet 3K feet or 10,000 meter almost. So you can get about 0 Celsius. Q high was 500 kilowatt. This is 5. If you see here, we have 1, 2, 3, 4. I can get everything. He wants determine W.net. He can ask for the eta thermal. Can ask for anything efficient or output for this Brayton cycle. If you want to remember, the Brayton cycle is like this, something like this, TS diagram. Usually we start from here, bottom left, 1, compression, isentropic, burning, constant heat, constant pressure, expansion, constant entropy, rejection, constant pressure. So pressure equal constant, pressure equal constant. This is Brayton cycle. Exactly the same as Otto cycle, but Otto constant volume. These two lines, constant volume. Everything Cp delta T. I wish to have temperature at every state. Because you have 4 things, you can get everything. Let's see one by one. You have 4 inputs, you have 4 processes, and you have ideal gas law, you can get everything for this. Let's start. Start with state 1. State 1. I care about temperature. I have P1, I have T1. I have P1 is 0, I have T1 70. So this is 70 kilopascal. This is 0, which is 273 Kelvin. This is the most important thing. I can get V1. If I want the internal energy into anything at this state, I can be done. Using ideal gas law, PV equal RT, I can get V. On R from table A to A. For table A to A, go ahead and get K, R, CP, CV for air. For example, if you want V1, it's RT1 over P1. You can get V1. For example, ideal gas law, PV equal RT. So everything is known as state 1? Yes. Why? You have 2 independent intensive properties. State 2. You remember, guys, how many times I said this sentence? Counterman. You remember? Are you counting on behind me or not? Or no? I hate this word. My daughter is killing me. You are saying that, Dad. So at state 2, we need 2 independent intensive properties. Counterman, count with me. Okay? Does anyone know how many times I said this?
82.
Seriously? Counterman is not, this is not the counterman. But anyway, so state 2. State 2, we need 2 independent, we need 2 things. So we have RP, which is kind of P2. So P2 is equal RP P1, like V2 when we do it in Otto cycle. RP is 10 times this, so 700 kilopascal. Oh, we are happy. We have 1 information at state 2. We need another one to be 2 independent. So what we can get to the guys at T2, at state 2, what we can do?
The P2 over P1 equal T2 over T1 to the power K minus, over K minus 1.
Perfect. This is called isentropic. 1 to 2 isentropic. Perfect. That's perfect. Isentropic for ideal gases is T2 or P2 over P1 equal T2 over T1 to the K over K minus 1. So P equal K over K minus 1, which is 3.5 for air. T equal, it's P over K minus 1 over K. That's why you have here K minus 1 over K. But anyway, so you can get here T2. Once you get T2, everything is done. Because you have T1 in Kelvin, you have P2, you have P1. So state 2 is completed. You can know everything about state 2. If you want V2, you want delta H, you want delta U, you want delta S, which is of course 0. For example, if you got this temperature and pressure, if you substitute back between delta S 1, 2, which is for example CV ln T2 over T1 minus, well, plus or minus ln P2 over P1. If you substitute, guys, what do you expect? what would it be? It will be what, guys? This is CP. I think this is CP. What do you think, guys?
Zero?
Here, zero, of course, because isotropic. If you put this temperature here and you have this and this and this, you can. We of course you will get zero because it's. So we got from this, we got this. Of course, it would be zero, definitely. So how about stage 3? Stage 2 now is completed. I care about temperature. That's why I boxed the temperature. So how about stage 3? What do you know about stage 3, guys? Let's take a break, yeah? About stage 3, guys. What we have. Look at stage 3. Look at the chart, TS diagram. What do you know between 2 and 3?
P3 equals to P2.
Exactly, B3 equal P2 equal 700. So during burning, you did not decrease a lot the pressure. It's almost the same. In reality, the pressure decreases a little bit. So when you burn, pressure a little bit decrease. You are moving along constant pressure line from 2 to 3. You add heat, the pressure almost the same between 2 and 3. So pressure 3 is 700 kilopascal. Perfect. I don't want to box it, I'm sorry. But how about the last thing? How can I get T3, guys? Can somebody tell me?
Q high is equal to
Perfect,
CP
you are great.
minus-
You are great. CP delta T. Perfect. I told you have 1, 2, 3, 4. You have everything. So Q high is CP M dot CP delta T. T3 minus T2 between 3 and 2. This is the combustion chamber. We have compressor, combustion chamber, we have turbine, we have rejection to the ambient. We don't have component, but we just dump in air and get fresh air. It looks like a cycle for us. So air is the reservoir. So we have CP, we have M dot given, we have Q high given, we have T2 from isentropic between 1 and 2. We can get T3, box it. It can be explicitly given or Q high. Last state, state 4. Almost done. What we have, guys, at state 4?
It's isentropic to 1.
Perfect. But before isentropic, what I have already before that, look at 4 and 1. What we have? P4 equal to P1. I need to have one information first. Then, as you said, apply isentropic between 3 and 4. Now, when you apply 3 and 4 isentropic, you will see T3 or T4, P4 over P3 equal T4 over T3 to the K over K minus 1. This is 1 over RP. This is 3.5. You have this, you have this, you have this. Actually, you have this, you get T4. Once you get T4, you get everything you want. For example, if you want Q high, which are actually given, CB delta T, T3 minus T2. If you want Q2, Q low, CB delta T, T4 minus T1. If you want this, it's Q high minus Q low. So this guy given, this guy, because it's kilowatt, M dot, CP. T4 I have minus T1. So the whole thing to get T4. If you want to get a thermal, that's actually must be required, but we can do it like 1 minus Q low over Q high. And you get it. You know what? Also, it's equal to that. You have RP equal to 10. You have K over Q minus 1, 1 over 3.5. Do this, guys, and do that. This is good check for you. You will, if you find the same thermal efficiency, let's say 50%, 49% from here and there, it means you are correct in all your calculation. Okay, let's take a 8 minutes break. Do you have any question, guys? You can, if you want, anyone want to leave for 8 minutes, it's okay. Do you have any question, guys?
Professor, when is the exam? The final exam?
It's on Wednesday. This
time?
Wednesday, August 12th, the same time.
Yeah. Oh, same time as class?
Yes, the same, from 10 almost to 1. This is the only class we go to beyond 1, beyond 12, because of the final. That's the final. And there is nothing in Friday, of course, so we have only Wednesday in the class from 10. I mentioned that in the syllabus, I guess. It was from 10, it will be from 10 to almost 1:30 for the submission. Okay, guys? Any
And
questions?
then does that mean we don't have lecture on Monday?
Monday will be a review 3, the last review.
I'll review 3. Okay.
So I'm gonna go again, say that read. Of course, you can from now listen to review 1 and 2 to cover from chapter 1 to chapter 7. So 1 to 5, 4 into 4, and a little bit of 5. It's review 1. Then from 5 to 7, review 2. Then review 3 will be focused from chapter 8 to 10. Okay? And we're gonna solve an exam.
You're doing a practice final?
What? Yeah, I'm gonna upload a sample final for you. It's about, I don't know, 17 problem. It's the same as yours. Yours are 16, I remember 16, 15 problem in 3 hours. Everyone like 10, 15 minutes, 10 to 15 minutes. Some problems 1 minute. If you know, like 2 minutes, 3 minutes, if you know the steps. Like I solve it in 2 minutes, I give it you for 10 minutes. I solve it in 5 minutes, I give you 15 minutes. So usually this exam, this is the way. You need to know a little bit the steps. You need
Will
to know
the final have extra credit problems?
of course. Even if it does not have, I always rescale. Like let's say you got a midterm 70. No, this is not 70. When I rescale, it can be go to 80. It can be 75. So as of now, I did not do any scaling. I'm giving you the grade as it is. Of course, would increase. Of course, even midterm 1, midterm 2, the final. So don't worry. Or you usually scale to make it better for you in the final grade. And also, if somebody get, let's say 67, I said, I'm gonna give him extra 3 credit to pass the class. You don't need to repeat it for just 3 credits. If you get 66, that's your problem. But if you get 67, if you get 77, I'll give you extra 3 to change your grade from C to B and so on. Okay? If you need some grade to change from one letter grade to another, of course I'll give it to you. That makes sense? Is it easy for you guys?
Yeah, thank you.
No worries, but please show me that you are working, guys. Please, all of you, do your best in the final. So if you did well, you will not you not did anything, and I will give you more. You deserve it. Yeah, you work. In the end of the view 3, I will post for you about 30 problems. The exam will be among these 30 problems. Let's say we have 60 homeworks, a lot of quizzes, a lot of, let's say all of that. We're gonna give you 30 problems. The exam will be mostly among them. Okay?
Sounds good. Thank you.
Okay.
Sounds
No
good.
worries.
Thanks, Professor.
No worries. Have a good. Let's take 4 or 5 minute break. Bye-bye.
The course of evaluation isn't open yet.
I know. I'm gonna contact the administration and see what's going on. I don't know why they're crazy doing a lot of things. I'm so unhappy with this semester. But anyway, we'll see. Okay, guys, let's take 4 minute break from me. Bye-bye. Inputs, you can get everything. I can replace this by T3. I can replace, for example, this by, for example, T2 and T3. So I give 4 information, usually state 1 and 2 other things. Pressure ratio, you can get everything in the cycle. Actually, with only the pressure ratio or compression ratio and cutoff ratio, you can get the thermal efficiency for Brayton, Otto, and diesel cycle respectively. So for everyone, if you have how much compression, if it's volume, pressure, if it's thermal, if you have all of these, you can get easily the efficiency. So this is good a check for you to make sure that all the temperature is correct. So this one, including T1, and T2 and T3 and T4, all of them. So you can get a good evaluation for your calculation. And of course, use this one. So both of them together work as a good check for you. So let's finish the last part, 9.10 for Brayton cycle. Then we talk about the last cycle in our course. Then take the last quiz 7. So Brayton cycle, guys, can be enhanced. Can be enhanced. There are 3 ways to enhance Brayton cycle. 9.10. We have something called regeneration or regenerator. We have reheating or reheater. This is 9.10. This is 3 ways to enhance the performance of an engine, Brayton cycle, usually jet engine. And finally, intercooler. All of these are to increase the efficiency, intercooler. Please follow me, guys, and focus in this last 50 minutes or 40 minutes in our course. The regeneration like this, we have compressor, and of course we have combustion chamber, and we have turbine. And of course, so we have 1, 2, we have 3 and 4. So if you plot it, we have 1, 2, 3, and 4. Sometimes T4, you reject here a lot of heat, a lot of heat. Somebody smart, he said, okay, how about this? If I do this, if I get this point, let's say 4, let's say 5. I got this heat, make horizontal and give it to this part. Take this heat, so he will get some heat from here using heat exchanger and pass it with this. This is called heat exchanger. Regeneration. Regeneration. So let's see the numbers. 4, and this is 5. And this is, for example, let's say 2 dash. This is 2 dash. So what happened? Instead of using the whole fuel here to burn from 2 to 3, no, I will take some heat from 4 to 5. 4 to 5, some heat. This is already dumped in the air. This is a lot of heat, especially if you have higher temperature difference. So T4 much larger than T2. If it is the case, I can take some heat from here, give it to here. Exactly this difference. Can take this heat, give it to this guy. To 2 dash. Then add heat Q high. Then I pay less. This is what I pay already. This part is what I paid. Then this part will drive this, then the remainder is mine. So I got pay less and dump less. This is Q low now. From here to here. This is called regeneration or regenerator. This is called what? Regenerator. Is it good, guys? Is it good? Clear? Is it clear?
Can you explain the 1 to 5 process again?
Okay. We have compressor. 1 to 2 compressor. If this is not there, 2 to 3 combustion chamber. I add heat from this point to this point. I pay everything here, correct? Correct? I pay heat for originally, what paying here from here to here. This is what I pay already, originally. Then I expand in the turbine, then I dump in the air. But we notice that some energy can be useful. This energy can be used to warm up the air here. So the heat can transfer from this side to this side. How? Take this heat, connect it to this using heat exchanger. If something is cold going through this pipe, something is hot going around, this is called heat exchanger, something like this. something is hot going here, something is cold going here. The heat transfer used through convection, we call it heat exchanger. Exchanger. The heat exchanger, I can use some of the energy from 4 to 5, then to heat from 2 to 2 dash. Why? To pay less from 2 dash to 3. Originally, I go from 2 to 3. Give this black. Now I took this, give it to this. Now I can go from 2 dash to 3. So I pay less. I pay less. Then get, so this is called regeneration. Use something was about to be dumped in the air. This everything was supposed to be dumped. No, I will dump less. Make sense?
Yeah, thank you.
Reheater, the same concept. We need to get more efficient cycle. Originally was compressor, combustion chamber, turbine. But I wish that I can go to the maximum divergence. Like if I can, I wish to go to like something like this, to get too much work from the turbine. From 1 to 2, 3 to 4, correct? If I wish this 3 to be 2,000, 5,000 Celsius or Kelvin, but this is impossible. Can I do that? No, it's impossible. We have material limit. We cannot go to this. Unfortunately, I cannot do that. I have maximum T3 here. This is like, let's say 1,200 Kelvin. The material cannot sustain after that. So I need to expand. Somebody smart, he said, okay, how about this? I'm gonna do something very interesting. I'm gonna come here, this is 3. I call this, for example, 4. Then I burn again. This is another constant pressure. This is pressure, constant pressure lines. Then I burn again. At a certain temperature, let's say T5, maybe less, maybe more. Then expand. So this is, let's say 5, sorry, 6, 4. So here I will add turbine 1, then add another combustion chamber, then turbine 2. So what happened here? I cannot go to higher temperature, but I can go, I assume here we have 3, 4 constant pressure lines. They are diverging, all of them diverging. Pressure 1, pressure 2, let's say pressure 5. This is 1 and 4 the same. 5 and 6 is the same. 2 and 3 are the same. I call it P1, P5, P2, for example. Then I compress from 1 to 2. Then I burn. I cannot go too much. I only go here. Then I expand turbine 1. This is turbine 1. Then I said, oh, how about this? Because the pressure line diverging, I'm lower than this limit. I can burn again. This is combustion chamber 2. So turbine 1, I make it, for example, green. I can get some work. Let's say drive the compressor and get some even extra work by burning again to go to higher temperature. So of course, which one is bigger, guys? This lens or this lens? Which one is bigger? Let's take another color. This one, the green color here or the pink color here? Which one is bigger, guys? Which one is bigger? The green or the pink?
The pink.
Of course the pink, but how come? What did I pay? I pay extra fuel here in the combustion chamber 2. This is combustion chamber 2. I paid extra fuel, I get hurt, so I got more. So this, I'm supposed to get this only, I get more. From here to there, let's say it equal this, so I get more. I got more by burning again. Burning. So some people do it a lot. Yeah, if you see some cycle like this. It's called regeneration. It's called what? So this plus this plus this plus this plus this until the last one. This is called what? The net or the turbine works. minus the compressor, and that you burn this, you burn this, you burn this, you burn this, you burn this. This is the maximum fuel you pay. This is called reheater. Sorry, reheater. Reheating. I'm reheating. Take that, reheat it again. Take the bar, reheat it again. Take it, reheat it. Take it, reheat it. Take it, reheat it, and so on. Got it, guys? Got it? Hey guys. Hello, hello. Is it hard? No one is following, guys? Are you following me
Yeah.
or no? So here we have intercooler. Last one. Intercooler, let's say we have compressor. Compressor is like this. And we have combustion chamber. And we have turbine. We know exactly that the pressure lines are diverging. Correct? Correct?
Yeah.
But it's also diverging if you go lower. Intercooler said, okay, go lower. It means you are here. This is the TS diagram. All of these plots, TS diagram. If you are here, I'm supposed to go from here to here. I said, no. I'm gonna go just something in between. Let's say 2 dash. Then I'm gonna cool down. This is another pressure, intermediate pressure. Then I will cool down. So 1 to 2 dash, then cool down. Then I compress again. Which one is bigger, this guys or this? This is bigger or this? Let's say this is 3 dash and this is 3. Actually, no, this is 1 2 dash. Let's take, no, maybe take numbers. 4. This is 5 or 5, 6. This is, for example, 2. Which one is bigger? 2 to 6 or 5 to this point? Say X. Which one is bigger? This length or this length?
Five to X.
It's bigger. This is bigger. I pay more or pay less? Do I want to pay more or pay less? I want to pay less. Then burn from here to 3. Let's say 3 is somewhere here. Then expand. So the cycle like this: 1, 5, 6, 2. So here I got this. I cool it down, then compress again. So this is compressor 1. This is compressor 2. This is called intercooler. This is cooling down. This is 1, 5, 6, 2, then 3, then 4. So 1 to 2, 3, 4. But instead of going vertically, I'm gonna cool down from 5 to 6. Compress some, then cool it. Does it make sense, guys? Why I did not cool down from here directly? Sometimes if you cool him directly, it may freeze, became like solid. Sometimes became like solid. But when you compress and cool, this temperature is greater than this, so it's not freezing yet. So you can compress. So you need it in liquid phase sometimes. Here is not a big deal, but for Rankine it will be a big deal. This is called intercooler. So what I save here is this. I save this length to be shorter, to be this length. So in the compressor, I pay less. This plus this, of course, lower than from here to here. So I take less in the turbine. To drive those, this plus this equal this. Then the rest is mine. If I compress directly, I will take less in the turbine. Because of this cooling, I pay less in the compressor. I reheat of the turbine. I used generation. I used some heat to warm up after the compressor. Let's talk about the last cycle, chapter 10. 10.2, 10.4, that Weber-Rankine cycle. Any question, guys, here? The last section, the last part before our quiz. Okay, guys. Ten, 2 to 10, 4. Rankine vapor cycle. The last cycle. It's exactly the same as Brayton. Exactly. But the only difference is steam flow. Exactly in power plant. You know, power plant, when we turn a light, this is usually this electricity coming from a power plant. We burn some fuel, we get electricity. So we have, usually we have pump, we have boiler, pump, we have turbine expansion. So it's coming smaller, became bigger. Then we have condenser. Then we have pump. So here 1, 2, compressor. Again, 1, 2, compression. 2 to 3, heat addition, boiler. 3 to 4, turbine expansion, get work from turbine. 4 to 1, condenser, go back to 1. Exactly same as Brayton cycle. This is very identical to Brayton cycle. But the difference is, Brayton cycle was for air, ideal gas, generally. Can be ideal gas, can be air, can be Rankine, refrigerant 134A, can be CO2, can be any ideal gases. Rankine, nope. Rankine is steam. This is the only engine we're gonna use a steam table. Steam table. This is the only engine like Otto, Diesel, Brayton, Dewell, Carnot. All of them were for gases, but this is the only one for steam. So when you plot it, you're gonna see, of course, the steam table. Like let's say the TS diagram. The same idea. Pressure line are diverging. We have one, and this is the constant pressure line. This is another constant pressure line. Let's say this one, and of course they are diverging. So what happened, guys? So what happened? Here I'm one. Before the pump, I compress. Everything is reversible. This isentropic, 0 delta S. Because it's a fluid, liquid, we assume constant even volume. So you can use the work in the pump minus VDP. We did it before. So the reversible work given in a pump, VDP. That's VDP. That's it. Because it's reversible and it's pump. Or delta H. Here I cannot see B delta T because this is steam table. Delta H. H2 minus H1. Everything is delta H. Then this is state 2. State 2 here. I'm gonna burn. Burn means I'm gonna add heat. Add heat. Let's take another color. What is the red? I'm gonna use the pink. So add heat from 2 to say 3. So 2 to 3, I'm burning at constant pressure. Burning here, isentropic compression, this burning at constant pressure. Exactly same as, but Brayton can constant pressure like this. Here, this is constant pressure like this. So Brayton is look like here in the vapor, superheated vapor of ideal gas. Then in the 3 to 4 expansion, go vertically. I can go maybe here. I can go maybe here. I can go maybe here. So vertically, it depends where is 3. It can go to here, which is not good. It can go to here, which is good. It can go to mixture here. So 4 can be anywhere. Let's say 4 was here, mixture. Again, this is constant pressure line. So what happened? I compress isentropically, burn, constant pressure, boiler, pay fuel, Q high. Then expand, turbine. I wish to go vertically. Then dump heat Q low, condenser. Then go back 1. Make it again complete liquid. Compress, burn, expand, condense. This is isentropic, isentropic. Of course. Heat compression and expansion, constant entropy. It means S1 equal S2. S1 equal S2. I cannot say anymore T over T equal P over P to the K minus 1 over K. I cannot say that because steam. Here I can say that. Here I cannot. Here I just say S1 equal S2. For more S1, steam table. Oh, actually here is 3, 4 because it's 3, 4 here. So 3 might equal 4. S1 equal S2 because it's 1 and 2. S3 equals S4. So let's say I give you 4 independent information. Let's say I give you P1, T1. I give you, for example, let's say the pressure ratio. So I give you implicitly P2. Let's say I give you, for example, T3 or the heat. I can get everything. I can get everything. Unlike Brayton, I said I want temperature. Here I want enthalpy. This is open system. This is open system, open system, open system, open system. Input, output, input, output. So always Q minus W equals delta H. Always. Here, W equals delta H. Here, Q equals delta H, Q high. Here, W equals delta H. Here, actually, here it was delta H, but delta H is delta T multiplied by CP. Here is delta H directly without even saying CP, but from using steam tables. Condenser, it's Q low. Delta H. Here is delta H. Here is delta H. Here is delta H. Here is delta H. W equals delta H. But here I can say delta H or VDP. If it had mass flow rate, M dot VDP. If it had mass flow rate. Why VDP? Because the volume is constant. Do you remember when I said if you have open system, reversible, and I compress it at constant volume, like pump, I can say W equal VDP. Comes how? Does anyone remember this? Does anyone remember this sentence? When you have an open system, steady, reversible, the work done reversibly VDP, the work always PDV. But if it's open system, steady, reversible, I can say VDP. Do you remember this, guys? In the end of chapter 7? No one remember? Now you remember. You know, what's his name? Trevor Noah? If you know, if you don't know, now you know. So W equal VDP. We almost gonna have quiz in 5-10 minutes. Okay, guys? W equal VDP. Guys, can you listen to me, guys? Can you hear me?
Yeah.
Yeah.
We can hear
So
you.
the work in the pump, VDP. Let's say you have P1, T1, P2, T3. I can get everything. It means I can get all the enthalpies. How? Let's take step 1. At 1, you have P1 and T1. You can go to the chart. You can get V1. You can get H1. You can get S1. You can get anything. Correct? Correct?
Yeah.
At 2, at step 2, you have P2. Of course, I give you pressure ratio, for example. I give you P2. And you have constant entropy. You have constant almost volume. So you can say you have S2 equal S1. And you even don't need this. The work done directly in the compressor, in the pump, sorry, equal just V1, which is constant, times dP, P2 minus P1. That's it. You don't need even anything at 2. At 3. What do you know at 3, guys?
What do you know at 3?
P is constant.
Exactly. P3 is constant. It's P2 between 2 and 3. What else? I give you T3. Correct? Correct? I told you I have P1, T1, P2, T3. So I give you already P3, T3. Correct?
Yeah.
Or I give you Q high. So Q high, which is H3 minus H2. You have H2. From H2 and Q2, you can get to H3, which means you have another, either you have T3 or H3. But now I give you, for example, T3. If you have two counterman, if we have two independent intensive properties, you can get everything. You can go to the steam table. I think this is table A6 for air, for example, for water. So you can get H3, S3, V3, anything. Correct? The most important thing in Solbus, H1, H2, H3, but we don't care about H2 much. We care about VDP. How about 4 guys? At 4. What do you know about 4 guys? If somebody tell me what I know about 4, I'll give you bonus 1 point in your grade.
S3 equals S4.
Exactly. What's your name?
Ethan?
Perfect. So this is isentropic. We don't use isentropic relation. We said S4 equal S3. So at 4, you have P4 equal P1 because it's constant pressure. And S4 equal S3. If you have S4 and P4, you can get everything. If S4 was between SF and SG of this pressure line, it's saturated mixture. If it's greater, superheat. If it's equal here, it's saturated vapor, and so on. So from this and this, you can get, for example, quality if it's mixture. You can get, for example, enthalpy, which is HF plus X HFG at this pressure. So if it can be mixture, it can be not. So the most important thing, I got the enthalpies. So this is just a special case for the pump. I don't need H2, but I need this. So if you, as you can see, I give you a problem. Can you see the problem, guys? It's a problem 1015. I give you P1. I give you T1, which is originally P1. With T4, I give you P2. I give you X4. That's good. I give you the pressure ratio, so you can get everything from this case. So I give you P1, T1. I give you P2. I give you X4. X4. So we can go a little bit backward. Forget about this now for a second. For now, if I want from you, for example, somebody tell me what is the heat here. If I want to get the heat here, equal to what? In the boiler, between 2 and 3, what is the heat?
Delta H.
Exactly. Q is m dot delta H, which is H3 minus H2. If it has m dot. If it doesn't have, put it 1. Just make it per unit mass flow rate, per unit mass. 1 to 2, the work is so easy. The work pump is V1, P2 minus P1. Usually, P2 is given, state 1 is given, but V1 coming from where? From ideal gas law? From where V1, guys? For ideal gas law or what? Huh?
Steam table.
tables.
Steam tables. Always a steam table. How about This is Q high. 3 to 4. 3 to 4 turbine. What is the work here, guys? W turbine. What's the work turbine, guys? Can I say M dot CB delta T? Turbine. Can you hear me, guys? Hello, hello.
H3 minus H4.
Exactly. H3. If it has mass flow rate, multiply by mass flow. If it does not, don't put it. Okay. How about the last one, condenser? Q low. M dot H4 H1. Now, if I want work dot net, you can say Q high minus Q low, or W turbine minus W pump. Both are correct. Correct, guys? Turbine minus pump or high minus low. They're the same. Which here, everything here, delta H. WQ, WQ. I think the problem is easy, guys, not hard. And if I want thermal efficiency, can somebody tell me what the thermal efficiency is here? What is thermal efficiency, guys?
Minus Q out over Qn.
Exactly. 1 minus Q low over Q high. That's it. There is no simplification here because we don't have any relationship like isentropic relationship or even enthalpy simplification like CB delta T. We cannot do that here. So just like this, or like the very minimum, you can say H4 minus H1 over H3 minus H2. That's it. This is a minimum. We cannot simplify more than that. So if you have the enthalpy everywhere, you are done. Again, if you have full information, let's say P1, P2, P1, T1, P2, T2, T3, or let's say X4. Like the problem, like this is not given. Let's say you have P1, P2, P1, T1, P2, X4. From 1, you can get everything like V1, H1, and so on. From at 2, you can get everything you want, but just this is enough. At 3 and at 4. 4 is known because this is, make sure you have this. You can get H4, S4, you can get anything you want. So the blue, let's say the black is given. The black was X4 and P1, T1, and here nothing, and here just P2. These 4 inputs, black. 1, 2, 3, 4. From this, you can get H4. You can get S4. You can get anything you want. S4 exactly equal S3. S3 equal S4. And you have P2 equal P3 equal P2. You can get everything here. You can get H3. Once you have H4, H3, H1, and everything here, you can get what you want. So W pump, just VDP. It's the easiest, fastest form. VDP, the pump. That's the only special case. The rest, delta H. Here is delta H, here is delta H, here is delta H. Here is heat addition. This is turbine, condenser. Compress, burn, or combustion, expansion, rejection. The same as Brayton. Brayton, we care about temperature. Rankine, we care about enthalpies. Is it clear, guys?
Yeah.
Hey guys, do you like my course, guys, or is you don't like it? Was I
I
that
liked
bad?
it.
Thank you. I'm not gonna give
Pretty
you bonus.
cool.
Thank you. Don't worry, guys. I'm not gonna give you bonus if you said you like it or not. Don't worry. Just that's it. I tried my best to make you guys, you know, as good as possible. Before I go in the review, hopefully we have lecture this Monday. I'm gonna give you like 15 minutes. Something so important. It's called I used to use the what is important here, like what do you care about. Let's say you finish this course, and you wanna, for example, see what did you learn. What did you? Oh no! Oh, they removed my questions. Okay, let me write it down again. Give me 1 minute, guys. I don't know why it does this. This system is so stupid. You agree, guys?
Yeah.
So I give you 3 problems. I'm gonna post it in 1 minute. Give me 1 minute. File upload. One of them is bonus. Okay, I think they are now available for you. Go ahead, guys. It's 11:40. It's like, I think 7-8 minutes to solve and 1 minute to. Can you see that question, guys? Quiz number 6. Does anyone not see the questions in quiz number 6?
No, it's not showing up.
No, I don't see it.
I don't see it either.
It says
So
it's for
open.
August 6th.
Oh, really? No, quiz 6 is August 6. Yes, it's August 6. Let me see. It's 11. It's available 11:36, which is already passed. Oh, wait. Oh, yeah, it's 50, make it 55.
There's 2 quiz number 6.
Those are the old ones, I think. I think this is quiz 7, no?
Yeah, I think this is the 7.
Give me 1 second. Sorry, guys, for that. It's quizzes, the Go quizzes. You see quiz 6, it's before, it's mentioned before quiz 4. You have 2 quiz 6. Can you see that, guys?
I think it's not showing up because it has the wrong date.
Okay, let me rename it.
Today's
Okay,
August
quiz
7th.
7. Actually, this is quiz 7. Questions are here and the dates are fine, the files. Okay, let's go to the dates. Can you see now quiz 7, guys?
Yes,
the
but it's
7th.
dated for August 6th and it's the 7th today.
Oh, yeah. I actually, no, my clock here is 6. Oh, I'm sorry. It's my
It's
bad.
okay.
No, I'm not kidding. I can take a screenshot. My computer is mentioned. I'm yesterday. I'm sorry. It's my bad.
It's okay.
It's now quiz 7 is available. I'm sorry. Actually, it's my mistake, not his.
Due yesterday, Professor?
Yeah. No. Quiz 7 now. Quiz 7. Open quiz 7, please. Can you see quiz 7? Now it's available.
Yep.
It's available till 55, but I'm sorry for that. It's my bad. I did not see that. Really, my screen mentioned Thursday. I can share screen, show you. Can you see that here, Thursday? Can you see that, guys?
Yep.
August 6th. It's my bad. I'm sorry. Anyway, go ahead and solve the quiz. I give you extra 5 minutes and take your time. I'm sorry for being late. So hopefully you will like the class. Hopefully you like the contents. I'm gonna send you one more blog. Hopefully you can read it in the weekend.